Shailendra Mathur from Avid, and Shailendra is presented in a few of the sessions that I've chaired in the past, so it's great to have him back. He's the vice president and chief architect at Avid. He's been awarded several patents and presented papers at numerous conferences, panels, and journals. With more than 25 years of experience in the media industry, he was one of the team members who received the Philo T. Farnsworth Primetime Engineering Emmy Award on behalf of Avid in 2018. And our second presenter is Narifumi Iwamoto. Iwamoto-san is a media technologist at Intel, serving as a principal engineer. He's been working on media codec optimization, performance optimization for over 20 years, beginning with MPEG-2, H.264, all the way up to the Intel video processing library. He's also an expert on camera raw processing and 4K, 8K, HDR technologies. Gentlemen.
Hello. It's noon, so I'll say good afternoon or good morning. I'm really pleased to have Iwamoto-san accompany me today from Intel, and we'll be talking about some of the work that we've been doing jointly as well. But first, I'm going to talk about some of the innovations that we've introduced in the VC3 codec family, the SMPTE VC3 codec family. First of all, I want to define what class of algorithms VC3 belongs in. Basically, it's mezzanine compression, and mezzanine compression, DNX is one implementation of it. ProRes is another example of mezzanine compression. There are others. But there are a few characteristics that I want to lay out compared to other codecs, for example, distribution, where you can have extremely high complexity computations just to get the extra bitrate savings that you need. Compared to that, mezzanine compression is made for editing, for post-production, and where you may have video servers capturing, you may have editing applications doing JKL editing, just jumping around. So the decompression of multiple streams is super important. Multiple streams, you might be doing multicam type of applications. So, and also the second aspect of it is that in your post-production pipelines, it can be on servers, any Apple or Intel or AMD-based machines. It has to work everywhere. So it has to be. So it's not. The target is not to be the interest in it as well for multiple reasons. There's already on macOS you have support on macOS through the video toolbox, but today Intel will also be talking about some of the work that they're doing as well. I want to point out a few things because DNX has been around for a very long time. And by the way, you'll see I'm interchanging DNX and VC3 because DNX is one of the implementations of the VC3 standard. So whatever innovation that we introduce on the Avid side or anybody else, we try and take it back into the SMPTE standardization, and you'll see other examples of that too. So the there's certain things that have existed for a while, and I just want to make sure that it's visible to folks. Things like people, when they use, say, DNX36 for offline editing, they think it's only 8-bit. No, it's 10 and 12-bit capable as well. You can actually capture HDR type of ranges in there, but of course the quality is not as good as the higher bitrate versions. We also introduced an uncompressed format. So for VFX exchanges, some folks had come to us and said, look, is there an alternative to DPX and TIFFs? So RDD50 in SMPTE was introduced for that. And last year we presented DNX GX, and I'm going to come back to that. Thank you. That is the right version. And then but what we're going to talk about today are basically 4 areas. One is the use in IMF. That has been standardized, so I'll just cover that quickly. Tunable bitrates is another thing that was asked for by a lot of customers, so we'll see the use cases. Then I'll show you some early results of something what we call DNX JD. That's a quality improvement that affects primarily the very compressed proxy bit rates. And then finally, Iwamoto-san is going to talk about some of the Avid Intel collaboration. Last year, we talked about DNX GX. I'm going to cover just a little bit of that, just enough, because it's actually important as part of it's a build up to some other things that DNX GX allowed us to do, or some of the work in VC3 that allowed it to happen. So what was DNX GX? DNX GX was built for those people who are exchanging very clean graphics. When you have very clean graphics, today, a lot of folks are starting to, but you need some compression, say at 145 megabit or even 36. But think of 145 megabit for HD 1080i. In those cases, what was happening is that people were using either ProRes 422 or DNX 422 codecs, because the QuickTime animation codec deprecated. It's still in use, but being deprecated, folks moved to these type of compressions. But guess what 422 does? Basically, the chroma sampling actually plays havoc. So part of the work that was done was combining one RDD50 and the original 2019 SMPTE spec to basically just allow for a 444 processing, even down to the very low level compressions. So at least for graphics, it allowed the preservation of quality. What's next for that is that last year when we presented it, we said, well, look, you got RDD50 and you can do and 2019, so join it together and here's an implementation. We're actually going to take this through a SMPTE standardization. That's already started now. Luis Barral in our team is just starting that process. So DNX GX will become part of the SMPTE VC3 spec. Now, VC3 and DNX in IMF. This has been a standardization that's been going on for quite a while. Why? A whole bunch of companies, especially part of the DPP, they have DNX as their current production format. They have lots of stuff in archives. Yet when they have to publish into IMF for broadcast deliverables, there's theatrical deliverables, but even broadcast deliverables, ProRes and JPEG, J2K exists. What that does is that you have to transcode to actually get out. That introduces 2 issues: cost and quality, and time. Right? It's actually 3 things. So the request was, look, if we have DNX material already and it's high quality enough, can we just pass that into IMF? But that required us to help those companies standardize. So we did that together with SMPTE over the last 3 years. And that, I'm glad to say, is finally finished. So for those folks who are who do work with DNX, you can pass this within IMF. It's a standard, but a lot of products still have to now start implementing to that before it becomes available to everybody. But just want to make sure that you knew that this was actually there as a standard now. Another innovation was tunable bit rates. Again, why? So a lot of customers came to us and said, look, we have, for example, DNX 145. Now, usually with any type of codecs, when you present a level, a profile, there's a bit rate associated with that. It makes it very predictable. But then there are times when you want to keep the same quality, and the quality is actually defined by the quantization table. So if you go from, say, in this case, DNX 145 would be SQ and LB. The quantization tables are different between them. But what if you wanted to keep the same quantization tables, but still be able to tune the bit rate so that you can go, say, 145 to 100 or 90, and these might be cases because of network shaping that you're doing. You want something to fit in there. So this is the problem statement that was actually brought up. So we did some work to allow for that, and that's been successful. And it actually works with the current VC3 standards as well. Now, the table on the right hand, on the other side, actually presents how far you can go. So traditionally, for example, 444 has been associated with 440, HQX with 220, SQ with 145, but you can go further down on the right hand side. But then we also have a suggested limit beyond which the quality is just not as good. So with some experimentation, those are recommended. Don't go below that, but at least some level of tuning flexibility is there now. So this is being developed. We've been trying it out, and we'll be releasing it as part of the DNX SDK. It doesn't require a SMPTE change because it's part of the encoding. However, the GX part changes things, because what was 444 before without GX is now available even to lower qualities, SQ and LB, and so those will go down. Those will also get tuned further, so you can go to lower bit rates. Another innovation that we've been experimenting with now is an improvement in quality. The term JD, marketing will kill me for putting it up there. It's not a marketing term. We don't know what it's going to be called. And over beers, I will share with you exactly where JD came from. It doesn't matter. But that's what we're calling it right now. What this was doing for us was, and when a lot of folks came to us saying that, look, at the highest compression level, there's blockiness that appears in continuous areas. So in this particular case, I mean, there's noise in the image, but then there's also the face where there's continuity. But yet that's where a lot of the compression artifacts, the blocky artifacts were appearing. Now you'll say, hey, well, that's a very artificial image, but I'll show you some examples later on. So we started analyzing what the DNX LB and on the left, on the other side, on my left side, there's blockiness there, which gets reduced on the right-hand side with DNX LB as well. So again, this is a noisy image. This is actually artificial, but it is part of the SMPTE, the bundle that we send out, that SMPTE makes available as part of the test images. Even though it's got white noise on the side, it is on purpose. But here's another one from the same sample set, which actually illustrates part of the problem, because in this case, the leaves and the stones almost look like the white noise. So what's happening is with the current algorithms, that's where basically less compression is being applied, and where people want to, where people's focus is in this case, this figure that's in front, that's where a lot more compression is being applied. Let me just jump to the next slide, which shows you that, again, the left, the one extreme is just uncompressed. The middle part is, again, with DNXHR LB. And what you'll see is that a lot of this, in fact, at a distance, what happens is that you see that not just blockiness, but also blurriness. That's another artifact because a lot of the blocks, because of the extra compression that's being applied over there, become so basically are only low frequencies. So all the low frequencies blend together to basically appear as a blurriness. GD improves upon that using the same algorithm. So I mentioned that it's to keep the bitrate, you have to make the compression go somewhere. Now, I'm not going to cover how the algorithm is built. There's a lot more detail in the paper that we published. So please do take a look. But basically, what we're trying to do here is rather than using PSNR as the thing that we're optimizing for, we're actually looking at the complexity of the different areas and optimizing for that. So the end result is what you see as a heat map, that the top right side, you see that's the current algorithm, where the stones and the leaves get a lot more attention from the bitrate controller, and so less compression is applied over there. Whereas the mid area, which is gray, the midtones, they actually get more compression applied to them. That's in the top one. But at the bottom one, in the end, what happens is that now what's darker is where you're getting less compression applied. And in the stone areas, you can see there's an optimization there too. So some of the results that you saw before is because of this different distribution of how you're applying your bitrate. So it's very intriguing. And where this is initial results, and where we want to take this is just start putting this. I mean, we've applied it on the SMPTE different images, the sample set that we have, but we want to collaborate with folks and see what happens with other image types. So we would like to introduce it and get some feedback on it. So now I'm going to hand over to Iwamoto-san. I'm so pleased to have this collaboration with Intel on all the optimizations. Iwamoto-san.
Okay, thank you very much. Thank you very much, Shailendra. Okay, thank you. All right. Let me prepare some things to you quickly. Sorry for stopping a little bit. Let me keep going. So my name is Narifumi Iwamoto from Intel. Coming here is to share our initial outcome of our collaboration in between the Avid and the Intel. So I was lucky to have an opportunity to join the project to optimize the DNX SDK, which is being redesigned for the BC3 based. So you heard about the BC3 from Shailendra already, which is a quality-oriented, very nice codec. But the next question is that how do we work on the existing platform? What is the user experience over there? Is that good or bad? So it's kind of important for us, right, to be productive. So then to answer that question, I have a kind of conclusion here in this presentation. Yes, we confirmed that the new DNX algorithm can fit with the existing hardware architecture very well, from mobile to servers. That is true. But today, so I just wanted to, share what we've done step by step, actually, by showing a couple of demos. So just wanted to share. Okay. Oh, sorry, man. They're kind of making a story with you. Let me, campus lock. I was a little bit, sorry. Okay, let me connect to the HDMI by this laptop with the HDMI cable. I have a huge laptop here. This is one such. Okay. Let me just go starting from here. Okay, this is an exact starting point. So that this is a real demo over this laptop. So there, but first thing, don't misunderstand. This is a kind of a DNX SDK or something. This is just a newly redesigned SDK. So that this is exactly the starting point we had. So that, okay, experience, roughly, you can see that, just 13, 14 frame per second over the UHD 422. Okay. So that, then we need to optimize it. So the how. So we actually analyze the performance bottleneck, by using the performance profiler called Intel Bitrate Performance Analyzer, which can show that the bottleneck at the instruction level and the software function level quickly. So that we identify the IDCT module was a bottleneck, which is kind of expected one. So then we decided to put the previously optimized module into the new SDK, but with the technology upgrade by using AVX, Intel Advanced Vector Extensions, which can operate that, more than 2x pixel at the instruction level simultaneously at once as compared to the previous SSE. So let me show you another one then. As you can see here the AVX on, so that you can now see that roughly 20 FPS from the 14 FPS at entire decoder level. And entire decoder level, I'm going to say roughly the 1.6x performance boost by using a new instruction set. So at module level, IDCT module level, this is actually the 3.7x to 4x. But still, so that at the entire decoder level, I'm achieving 1.6x. This is not, this is actually the big deal. But actually not enough, right? So, still the 20 frame per second, which means the single decoder takes 50 milliseconds over this laptop. So then next strategy is, what is the next strategy? So of course, the single module is well optimized. So let's try to scale it out to the multiple cores, right? Yes, that's a multi-threading, but multi-threading is not actually easy because one is, just a synchronization, dependency difficulties. Second is the operating system dependency. So the software is going to be very complicated actually. But Intel has that answer to that. So we have a, thread building block library called Intel 1TBB with very few line change of code over there. So then we apply that multiple threading over there. Let me show you the final demo. Okay. Now this one is thread 22 thread over there. As you can see, roughly the 100 up to the 100 now. So I am taking advantage of the entire core now. So okay, it's actually good. So that is optimization, it's not easy actually, but by using a couple of tools like Bitrate Performance Analyzer and 1TBB, so that you can relatively, easily achieve that higher performance. So lastly, let me show you one more thing. I have, okay, this one. I am actually driving with a battery model here in the laptop. It's just HDMI cable only, right? Let's try to connect it. Power now. Go down. What happens after that? So that's a question. Okay, over the 180, close to 200, almost 2x as compared to battery mode. The reason is because, the performance core frequency can go up by using the power if you plug it out. So then the frequencies are a little bit down just because to save the battery, right? So that's a huge difference. If you try to see that web browser, you will not see the differences, but the power on has a huge differences actually. We can achieve now 200 over these laptops. Yeah, this is all what I have. So please stay tuned for the next, our collaboration. Thank you very much.
Sorry, I thought I turned it off. Thank you for that, Iwamoto-san. Now, what was being shown right at the beginning, just the 20 frames per second, this is a brand new, basically we were trying out completely unoptimized to optimize, analyzing the power, what happens with laptops. I think the previous speaker talked about the green initiative. But when you're in the field as a news editor, walking around with a laptop, we need to analyze all of this, like completely power off. Everybody needs to be aware of these different profiles. On a powerful workstation, plugged in, power there, multiple cores, you can go up to we measure 40 to 50 streams simultaneously on the same desktop. So these are all, but on a laptop, it can vary. So so we're working with Intel to not just figure out the current profiles, but also the newer generations of the desktops and laptops that are coming on. What advantage can be taken of all of this work? So, and that's basically just the yellow highlight, basically the IDCT module we saw with the AVX instruction going up by 3.7 and double the DNX, and then scaling went up to 20x in our internal work, and that's what's in the paper as well. Just to conclude, we'll continue this performance fine-tuning, working with Intel, working with others, but there's a lot more performance still to be had, especially with newer generation hardware that's coming in, SoC, converged. There's a lot of architectures coming in to take advantage of. There are a couple of new areas I would love to invite collaboration on. We're being asked, very similar to JPEG 2000, is there a way to just serve up the same quality but at scalable? For example, in a web browser, I just want to quickly see a very low quality image. Is there something we can do? I know other codecs, we can do that, but rather than switching codecs, folks are asking, is there something possible? We see a few opportunities there, but again, it's in research stage, so would love collaboration on that. And we're constantly be asked is, how low can you go? DNX 36 at 24 frames per second HD is what it's at right now. But interestingly, there are new technologies coming around. Last year, we presented semantic region of interest as an AI application area. Could we take that and apply that to, just to get extra compression? Are there other tactics coming along? So again, this is also another area with the Intel and others that we're working on, but invite collaboration. So VC3, DNX, you can see lots of innovations coming in constantly last year, this year. So really pleased with some of the progress on that side. Thank you very much for your attention.